Greetings everyone, Professor Simon back for some more Calc 1. Now it's time to bring all of the stuff we've been talking about since this new unit and talking about integrals and areas and summations, bringing it all together. The fundamental theorem of calculus. It's not named that unless you get the idea that it's really important, right? The fundamental theorem of calculus. It has two parts, and it shows exactly the connection that we needed in order to bring together all of the ideas that we had from derivatives into all of the new ideas that we need for integrals. Part 1, if some capital F function's derivative is a little f function, right? This is just the names we're using, what they use a lot for these. Then the integral from a to b, the definite integral from a to b of that little f of x dx is equal to capital F function evaluated at b minus capital F function evaluated at a. This is a small link to two huge concepts. At the very beginning, we talked about antiderivatives. Remember, we use the integral symbol like this as one of the ways to denote that I was going to do the antiderivative from one piece to another to get to the answer that was an original function. Now we're bringing together the fact that the reason we're using the same integral symbol with the numbers to represent the signed areas that we've been adding up is because they're actually going to be one and the same. Okay? So if something is an antiderivative, in other words, the antiderivative of little f is big F, according to this statement right here, because the derivative of big F is little f. So if I take the antiderivative of little f, but then also have these boundaries between a and b, then I find the antiderivative, the big F function, and then I plug in the b value, subtract, plugging in the a value. The proof of this is very well written in just about every calculus text, and it's even in the OpenStax book. It has to do with writing these two values in sequences of the rectangles that we've used, and then it relies on the derivative mean value theorem that we've seen a long time ago. So the mean value theorem is quite important for showing that the fundamental theorem of calculus is true. Okay, so here's the lowdown on it. Here's the example. Since I can show from a couple of sections ago that the antiderivative of 4 minus x squared dx is 4x minus 1/3 x cubed plus c, right? I'm just using power rule here. Antiderivative of 4 is 4x. Anti-power rule here, I add 1 to the 2, divide by the new power. And of course, with every antiderivative, you add a constant plus c, right? Then, what we say is the definite integral from 0 to 4 minus x squared dx, I'm hoping you're recognizing this one, right? This is the one we used a bunch in the last lecture or two, okay? Now, instead of doing the limits of the summations to perform this definite integral, I simply find the antiderivative, which we just did, and then we symbolize evaluating it between the top and the bottom values with these brackets. What I do is I say, okay, I've already performed the integral, the antiderivative, so notice there is no integral symbol here. I put the square brackets around it to designate that I'm going to be plugging in some values now. That would be the 4 and the 0. Also notice there's no plus c here. That's okay, because think about it. If both of these pieces here had plus c's, it would be plus c and then minus c. Okay, so the actual constant of antiderivative action doesn't matter when doing a definite integral. Okay, it basically would just wipe out to 0 anyway. So I don't bother. Right here, if I symbolize it like this, then what's going to happen is I always plug in the top minus plugging in the bottom. So when I plug in the top, that's here, 4 times 4 minus 1/3 times 4 cubed, minus plug in 0, 4 times 0 minus 1/3, 0 cubed. Notice all of this is going to be 0 though, so all of that's gone. And then 4 times 4 is 16, 4 cubed is 64 over 3. And that should look familiar because that's the two things that we got to add up when we did the limit and the summation. Negative 16 over 3 is that same answer. So instead of having to write our definite integrals as limits of summations and then having to deal with how to simplify that summation, which, as you recall, we only did for x to the 1, x to the 2, and x to the 3. Anything beyond that, there's all kinds of crazy rules, if you can even get a crazy rule for some of the things like sines and cosines and logarithms. Okay, so forget about all that. Now we have this. The first part of the fundamental theorem is, here is how you can actually evaluate those definite integrals, right? To find those signed area regions, or the total signed area sums over intervals on the x-axis. Okay, all of those properties, by the way, of definite integrals that we talked about before are still valid. If you want to flip the a and the b, you got to bring out a negative. If you want to split a and b with a number that's in between, you can add two integrals from a to c and from c to b. All of that still counts. Okay, this is something that comes along by coupling the mean value theorem along with all of the limits and the summations that we had already. So I've got this nice, neat way of performing definite integrals now. All I need to be able to do is an antiderivative and then plug in the top and the bottom values and subtract. Okay, that's it. That's how you perform a definite integral. The indefinite integral is still the same. Back from the first bit when we were talking about it, this is not going to change. We're still going to symbolize this as taking an antiderivative. And then this is an application of being able to do the antiderivative, right? We plug in the numbers. Just like with derivatives, we have certain problems where we just find a generic derivative function. And then we have other applications where we want the derivative at a location. Except with an integral, it's not at a single location, it's over an interval, right? So you still have the two different sides of the coin here, right? You have the function side and you have the evaluation side, all right? That's what this ends up being. Part 2. This describes in more detail the relationship between derivatives and integrals, okay? And you need to be kind of specific. They're supposed to be opposites, right? Because I'm using an antiderivative with an integral symbol. Sure, yeah, they're inverses, they're opposites, if you define it the right way. Notice the way this is defined. If capital F of x is a function of x such that x variable is in the integral, not in the f of t here. F of t is just our structure, and dt is our counter variable, kind of like with the summation. The dt is only there because I'm doing an integral. I need some variable to just keep the integral together and to be my counter in the integral. But that t doesn't actually do anything for this function. The t is just how the integral is adding up all the function values. The x is the boundary number. So when I take a derivative of this capital F, all I get is the little function f evaluated at x. Okay? So let's get a couple of applications there. Let's say g of x, capital G of x, is equal to the integral from 3 to x of 4 minus t squared dt. Look familiar? It's the same one as over here, right? So I take the antiderivative and I get 4t minus 1/3 t cubed. It's the same antiderivative here. I'm even doing the same integral setup. It's just that my boundaries now are not the same numbers. They're 3 and x. But remember, the way we evaluate that is top minus bottom. So I plug in x, and I plug in 3, and I'm just calling it some constant, because I don't care what happens when I plug in 3. It's, 12 minus 9. It doesn't matter. It's some constant, okay? Because I don't care what it is. Now that I've actually figured out what capital G of x is, take the derivative of it to finish this theorem out. G prime, the derivative of 4x is 4. The derivative of x cubed is drop you 3. 3 times a third is 1. So I get 4 minus x squared. It's just as the theorem stated. If you have some function defined where x is the integral boundary, right, then the derivative is basically the inverse of that operation. Okay? Think about why that has to make sense. The function here is not the thing that I'm trying to invert. The derivative needs to be the inverse of the integral itself. So the thing that I'm taking the derivative of, if I were doing d over dx, needs to be attached to the thing that the derivative should eliminate with. In this case, the integral needs to be connected to x, right? So not in here. The x needs to be part of the integration process. So when I do my derivative, you'll notice it's the same function, 4 minus t squared, 4 minus x squared. It's just now the x is evaluated in that function. Okay? Now, do we have to go through this process every time? No. I was just showing you that it does work. Here's how the process should go. If you're handed a function, capital F of x is equal to the integral from 5 to x of t over t minus 1 dt, then the derivative f prime of x, according to this theorem, should just be this function, little f of t, but with x plugged in. So instead of t over t minus 1, it's x over x minus 1. And that's it. That's the relationship between derivative and integral. They are opposites, but they need to be opposites in the way that the integral boundary is the thing that you're taking the derivative of. As the boundary changes is what this really means, okay? Another way of looking at it, remember, derivative is like taking a little bitty slice, right? And looking at one tangent line piece, one little slice, right? Well, with an integral, you're adding up a bunch of slices. Remember, we add these things up to get that area underneath. So if I take one little slice out of a list of slices, then what I should get is the function itself that's generating the slices, right? Hence why the variable needs to be part of the integration. And that's why these two things would be opposites of each other. Derivatives take a single slice. Integrals bring together all of the slices from one end to another, okay? Integrals sum up. Derivatives break apart. They're opposite operations. And these two, part 1 and part 2 of the fundamental theorem of calculus, basically take advantage of those things so that we can do most of these calculations. You'll be using this part more than the other one, but this relationship between derivatives and integrals is crucial. First round of examples. Let's do some of the part 2 integral function, finding the derivatives of those functions, right? So I've got 3 integral functions here. Now let's find the derivatives of each one. Remember, we needed to have x as the upper bound in our formula for this thing, and it's backwards here. So the first thing I'm going to do is I'm going to rewrite it using my definite integral properties, which, if you remember, I would just get the opposite of the integral from 5 to x now. Still 3t squared 6th minus 2t to the 4th plus 4e to the t plus 1 dt. And now my rule from before applies, right? If I want to find the derivative of this, so dA dx, we can write it that way too, it doesn't have to be with the prime, would be equal to negative, don't forget the negative, 3x to the 6th minus 2x to the 4th plus 4e to the x plus 1, like so. And then, of course, at this point, if you wanted to, you could distribute the negative if that makes you feel better. But this is just fine for our derivative here. Now, b of x. Looks like a straight up setup before. I don't have to switch anything. But wait, there's something else other than just x in there. X is a function inside of a function now. Not just x, I mean the thing that has x in it is also a function. It's not just x anymore. Well, that's okay. That just means it's a chain rule, right? Because I have a function inside of another function, right? 4x squared is a function as the inside, and the outside function is the integral. Okay, fine. So if I'm going to do my derivative, b prime of x is going to be equal to, just like we said before, right? This stuff, whatever's in here, just gets replaced for the a's. So I get 4x squared over 4x squared minus 1. Now chain rule times 8x, because the derivative of 4x squared is 8x. So let's simplify. b prime of x is then equal to 32x to the 3rd over 4x squared minus 1. Okie dokie? So the actual interaction of the derivative and the integral, right, that's pretty easy. It just basically falls apart. Okay, next. Now, this time, not only do I have some chain rules going on, but the x is in both limits. How do I handle that? Well, according to our theorem over here, the only way that's going to work is if you are, having a number in the bottom there so that I can wipe that piece out, right? Okay, so then the way this is going to work is I have to split this into two different pieces, right? I have to say that capital H of x is equal to the integral from some number. You know what? I don't even care what that number is. Instead of hashtag, I'll pick something like gamma. 3e to the 5x square root 1 minus t squared dt plus the integral from cosine x up to gamma. Now, the only stipulation here is that I'm picking some number that's in between these two. So in other words, you pick some x value, and this value, you just want to pick it's in between. Actually, you could even get a little bit less rigid with that and say, well, you can pick almost anything. As long as the function itself can be defined on the inside, really is what you're picking here. Okay? But it's the same value both spots. Square root of 1 minus t squared dt. Okay, great. This one's ready to go. But this one, the variable is in the bottom, and I need it to be in the top. So using my other, like I did over here, using my other properties, I still have from gamma to 3e to the 5x, square root of 1 minus t squared dt. But now I have minus integral from gamma to cosine x, square root 1 minus t squared dt. And of course, rules of derivatives say that I can, split it over subtraction. So I'll do just the derivative of this one and just the derivative of that one and keep the negative sign in between them. Okay, so h prime, or dh dx, is going to be equal to, here, the square root of 1 minus 3 squared is 9. And then e to the 5x squared is e to the 10x. You know what? I'm going to put a little bit of space up here. Hang on. Hang on, hang on, hang on. I'm just going to write it out one step at a time. 3e to the 5x squared. And then the inside derivative is 15e to the 5x, because e to the 5x is its own derivative, but you drop out a 5 from that inside chain rule, and you get 3 times 5 is 15. Minus the derivative of cosine is negative sine x, and then I have the derivative of the integral portion is the square root of 1 minus cosine squared x, like so. All right, so let's simplify a little bit here. H prime dh dx, whatever way you want to write it, h prime of x is equal to, I have 15e to the 5x square root of 1 minus 9e to the 10x. Because here, 3 squared, right, is 9. And then here I have an exponent raised to another exponent, which means you multiply them. So I get 10x. Double negative gives me plus sine x, right? That's this derivative piece here. But then also don't forget 1 minus cosine squared, right, is sine squared, right? And I've got square root of sine squared. What do you think that's going to give me? Almost. It's going to give me sine, sure, but remember, sine can take on negative output values. And square root and squared, when mixed together, actually don't just give the object back, they give the absolute value. So it would be times the absolute value of sine x, like this. And that would be your derivative function there. Now let's get some more examples, but this time with the other part of the fundamental theorem of calculus. Yes. So here, I've got 4 definite integrals that we need to do this time, and we won't be using limits of summations. Let's do the antiderivative versions using the fundamental theorem of calculus. Okay, so start by noticing, yes, I do have an integral. That means I'm doing an antiderivative. So then I see my object, and I'm going to take the antiderivative. Since it's definite, I won't bother putting the plus c. If I didn't have the numbers here and it was indefinite, I would be putting the plus c every time. Okay, so I start with a bracket. Antiderivative of x to the 3, 1/4 x to the 4th. Minus 5/2 x to the 2, and minus 4x. Evaluated from x equals -2 to x equals 3. Now remember, to evaluate it, we always do top minus bottom. Okay? Now here's the thing though. You can actually do it a couple of different ways. I could take the 3 and plug it into everybody, then take the -2, plug it into everybody, and then subtract those 2 big values. Or I could actually look at these as each individual antiderivatives. And I could do 3 and then minus the -2 just right here, and then plug in the 3 minus the -2 just right here. And then it just depends on which way makes more sense to you at the time. For this one, I'll just do the first one I said. I'm going to plug 3 into everybody, then plug -2 into everybody, and then we'll simplify. Okay? So let's see. This is going to be equal to, if I plug in the 3, 3 to the 4th is 81/4, minus 3 squared is 9 times 5 is 45/2. And then 3 times 4 is minus 12. Minus, top minus bottom, right? This minus is because of the fundamental theorem. I'm plugging in negative 2. Negative 2 to the fourth is 16. Divided by 4 is 4. Negative 2 squared is 4. Divided by 2 is 2. Times 5 is negative 10. And then negative 2 times negative 4 is plus 8. Okay, that's great. So let's see what we've got going on here. I'm going to get some common denominators between these two first to see how bad it's going to be. 81 fourths minus 90 fourths, right? And then I've got negative 12 minus 4 plus 10 minus 8. Notice you could have added up the pieces first and then put the negative on it. Either way, it doesn't matter, right? Okay, so then I've got negative 9 over 4. And then I've got negative 16, negative 24, negative 14, right? Okay, so since they're both negative, I will be adding these together and keeping the negative. 4 times 14 is the same thing as 7 times 8, right? 56. And then plus the 9. So negative 65 over 4. Okay? No big. Plugging in a bunch of numbers. Next, antiderivative, or actually I should say definite integral from 1 to 8 of the third root of x squared plus 1 over x squared dx. Fine. Right here, I'm going to notice that what I have is, this is x to the 2/3 plus x to the negative 2, right? That's what each of these are. Now, I haven't done any calculus yet. I have not done an antiderivative yet. That's just me rewriting them so I can use the power rules, right? All right. So here we go. In fact, let me do this in blue so it won't mix up with the other. This is going to be equal to, I'm doing the antiderivative now. 2/3 plus 1 is 5/3. If I'm going to divide by 5/3, because remember you get your new power, divide by it, that's the same thing as times 3/5. Okay, plus x to the negative 2, add a power, that's x to the negative 1. Divide by the new power, divide by negative 1, that's just going to give me minus. And then this is going to be evaluated from 1 to 8. All right. So now I'm going to plug in 8 into x to the 5/3. So that's going to be 3/5 times 8 to the 5/3. Okay, so 3/5 times 8 to the 5/3 is 32, right? Because the third root of 8 is 2, and then 2 to the 5th power is 32. And then 8 to the negative 1 is just 1 over 8. Minus the bottom, so if I plug in 1 to any power is 1, that's just 3/5. Minus 1 to the negative 1 is 1 over 1, so just minus 1. Great. So here I've got 96/5, and I've got minus 3/5. I'll go ahead and group those together. I've got minus 1/8, and I've got plus 1. Okay, so 96 minus 3 is 93/5. And then I've still got the minus 1/8 plus 1. So let's see, common denominator for everybody now is going to be 40, right? So then I'll have to do times 8 here, which will give me 744 over 40 minus 5 over 40 plus 40 over 40, right? Okay. So then 40 minus 5 is 35 plus 744 is going to be 779 over 40. Yum. Yum, 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 yum. Yep. Let's see, 14 and 9. Yeah, no, that doesn't add up to anything that's going to be divisible. Let's just leave it like that. Very good. Okay, next. Definite integral from pi over 2 to 0 of 2 sine x plus 3 cosine x. Now I want you to notice that the interval here from pi over 2 to 0 is actually reversed the way we usually count. And if you remember back into the last lecture, I mentioned to you that antiderivatives, definite integrals, are a directional operation. They deal with signed areas as well. So going below an axis or reversing the direction that you're counting always causes some sort of negative or opposite to happen. And notice I could go ahead and bring that out if I wanted to. If I wanted to just reverse these back to normal, right, from 0 to pi over 2, I would have to put a negative there, right? So it gives me that reverse direction. I'm not going to bother with it because it'll take care of itself. I'm just going to do my antiderivative, and then I'm going to do the top value minus the bottom value, just like before, because it's just extra work and more writing to put that extra step in. Okay, so equal to, my antiderivative of sine is negative cosine, plus the antiderivative of cosine is sine. And then it's evaluated from pi over 2 to 0. All right, so then this is equal to, I have negative 2 cosine of 0. Cosine of 0 is 1. So that's just negative 2 times 1. Plus 3 times sine of 0, which is 0. 0 times 3 is 0. Minus pi over 2. Cosine of pi over 2 is 0. Plus 3 times sine of pi over 2 is 1. Like this. So it looks like what I'm getting is negative 2 minus 3 for a grand total of negative 5. Alrighty. Next, the integral from pi over 6 to pi over 4 of 1 over 1 plus cosine x. In a previous lecture a couple of times ago, we were talking about antiderivatives. We handled one very similar to this. So let's go ahead and do this one the same way. I'm going to try and rearrange this thing because I don't have any kind of a quotient rule or anything for antiderivatives. I'm just going to rearrange it using some trig. I'm going to multiply the top and the bottom by the conjugate of the bottom, 1 minus cosine x. So then what I end up with is the integral from pi over 6 to pi over 4 of 1 minus cosine x over, now real quick, remember that when you multiply conjugates, you get a difference of squares. I'm going to get 1 minus cosine squared x from this multiplication. Okay? I did that on purpose because I wanted to be able to simplify this. 1 minus cosine squared is sine squared. And dx is still there. All right. I'm going to distribute the sine squared underneath each of these pieces. Now that the denominator is a single term, that's a good way of separating out difficult pieces. So what I now have is the integral from pi over 6 to pi over 4 of 1 over sine squared, which is cosecant squared, minus cosine over sine squared. Okay, let's talk about that one for a second too, right? Cosine over sine squared is the same thing as cosine over sine times 1 over sine, right? Cosine over sine squared is going to give me this. I can split that way. I could write it as cosine over sine squared, but I know that cosine over sine, cosine x over sine x, is cotangent x. And I also know that 1 over sine x is cosecant. So what I have is cotangent x, cosecant x, dx. And that's actually very lovely because both of those are derivatives of some of our trig functions. These are going to be straightforward antiderivatives. The antiderivative of cosecant squared is going to be negative cotangent x. And the antiderivative of negative cosecant cotangent of x is cosecant of x. And this is going to be evaluated from pi over 6 to pi over 4. Alrighty. So then let's start plugging in some values, right? Cotangent of pi over 4 is 1, right? Because tangent pi over 4 is 1. Cosecant of pi over 4. Well, remember, cosecant is reciprocal of sine. Sine of pi over 4 is square root of 2 over 2, or 1 over square root of 2. And so cosecant is the reciprocal of that, so that would just be square root of 2. All right, minus, plugging in pi over 6 for cotangent. The tangent of pi over 6 is 1 over square root of 3. So this is just going to be negative square root of 3. Plus cosecant of pi over 6. Well, sine of pi over 6 is 1/2. So cosecant pi over 6 is 2. Okay, so let's see what we've got here. I've got negative 1 minus 2. See it? Minus 2. So that's a total of negative 3. And then I've got plus the square root of 2. And I've got plus the square root of 3. And that's it. Unless you want to go, punching the rest into a calculator and getting the approximate value, that's as low as you're going to be able to bring that one. Okay? So the other piece of the fundamental theorem of calculus gives us the way in order to evaluate all of these different definite integrals, as long as I know how to take an antiderivative. Another side application, of course, that's going to come up is let's find the average value of some function. Now that I can do the definite integrals without as much trouble as all the limits and summations and everything, right? I can find the average value of something quite quickly. So let's do that. If I'm going to average this function, right, then I'm going to have to compute average value is 1 over 3 minus 1 times the integral from 1 to 3 of our function 4x plus 5 over x cubed dx. Right? So there's our calculation setup for the average value. Right? Just following the formula is all I'm doing. 1 over 3 minus 1 is 1/2, of course. And then I've got the integral from 1 to 3. And I don't like the quotient setup on this one. So what I'm going to do is I'm going to split the x to the 3 between each of these two pieces. That's going to give me 4x over x cubed, which is just 4 over x squared, plus 5 over x cubed. Okay, next I will rewrite these as something that I can use a power rule with. That's 4x to the negative 2 plus 5x to the negative 3. Now, this is going to be equal to, I'm going to do my antiderivative. Don't forget to bring your 1/2 with you, right? The 1/2 is still there from doing the average. I've got the antiderivative of x to the negative 2, which will be x to the negative 1. Divide by the new power. That will give me negative 4, right? Because it'll be 4 divided by negative 1. Plus x to the negative 3. If I add 1, I get x to the negative 2. And then I divide by the new power. I'm going to divide by negative 2. So that's going to be minus 5 over 2. And then this is going to be evaluated from 1 to 3. So let's see. This is going to be equal to, I've got my 1/2 times the whole thing. Let's plug in 3, right? 3 to the negative 1 just puts 3 in the denominator. You know what? Let me write this out a little bit more. This is going to be negative 4 over x minus 5 over 2x squared from 1 to 3. Let me just rewrite it like that so it'll be more visually obvious what I'm doing here, right? Because I'm just putting my negative powers, putting them back into where they're supposed to be. Equal to 1/2 times, now top minus bottom. I plug in the 3, I get negative 4/3 minus 3 squared is 9 times 2 is 18, so 5 over 18. Minus bottom, right? So that's negative 4 over 1, negative 4, minus 5 over 2 times 1, just minus 5 over 2. Like so. All right, so let's see. I have a 2 denominator, I've got an 18 and a 3 denominator, and none of it is like enough to combine at this moment, right? So I'm just going to go ahead and get a common denominator through everything. I'll have my 1/2 times, and then everything will be over 18, right? Okay, so 3 times 6, that's going to give me a negative 24, minus 5, because it was already over 18. Double negative, so that's going to be a plus, right? 4 times 18 is 72. Double negative again, right? So plus, and then times 9 to get to 18, so that'll be 45. Here, now I can do the multiplication in the bottom since they're singular, right? My denominator is going to be 36. And then I've got negative 24 minus 5, which is negative 29. And then 45 minus 29 is 16, plus 72 will give me 88 over 36. Let's see, I can get a 4 out of both of those, right? So that's 22/9. Let's finish up with one more example of the connection between an antiderivative and a derivative function through a graph this time, right? Okay, so we have this little g function right here. Sorry, I should have labeled it. This is little g of x, this blue graph here, okay? Little g of x is defined on the closed interval from -6 to 12, right? So little g of x, and x is going to be on this interval. Okay, as you can see, g of x is completely continuous on this interval. Now, big G of x is defined as the integral function of the little g function from 0 to x. So in other words, whatever number gets put in, that's the upper bound of my integral. So it's an integral function. Since I don't actually have an equation for little g, I have to leave my definition like this. Okay, so it's okay though. Remember, the definite integral we can associate with signed areas, right? Okay, so now let's answer a few questions. First, g of 0. Well, that would be the integral from 0 to 0 of little gt dt. By the way, don't let it throw you off that this is t and dt and this is x. The generic definition of x, right, is just because this is our x-axis. But you can say it's g of whatever, right, and just replace it. I needed t as the dummy variable for the integral, and that's all. Okay, so anyway, back to this. One of our integral properties that we probably should have mentioned is that anytime you have a definite integral from one value to itself of any function is going to be 0. And that's because you have no interval, right? The interval from a to a is going to have length 0. So then the answer to this is 0, right? So big G of 0 is 0. All right, what's big G of 12? Big G of 12 is going to have to be the definite integral from 0 to 12 g of t dt. Well, I don't have anything to punch in with my fundamental theorem, but I do remember the connection that we made in the last lecture of being able to do the signed areas to get these definite integrals, right? So here I go. From 0 to 12. So I just need to figure out these little areas in here so that I can add them up and get the total signed area, right? So I've got this little triangle right here, right? This triangle right here, whose area is going to be 1/2 3 times 3, or 9 over 2. So I have a plus 9/2 here, right? Because that's a positive area up above the axis there. Next, I've got this region, but it's below the axis, right? And I'm going to split it into two triangles here. This is a 3 by 3 triangle again. So this is minus 9/2 for the same reason that that's plus 9/2, right? Inside of this little region right here. Because it has a base of 3 and a height of 3 again, but it's below the axis. On the other side, I have a height of 3 and a base of 6. So the area for this guy right here is 1/2 times 3 times 6, or just 9, okay? But negative 9 in this triangle region here, okay? So then, if I'm doing the integral from 0 all the way to 12 in this particular problem, then that means I'm going to be doing 9/2 minus 9/2 minus 9 for a total of negative 9. Okay? What about g of negative 5? That would be the integral from 0 to negative 5 g of t dt. All right? To facilitate what I've said before, the integral is a directional calculation. I'm going to flip this the normal way, and it's going to pop out a negative. From negative 5 to 0, g of t dt. Okay, so now that it's in the proper order in the way that we read, I can again use the signed areas to qualify this thing. Okay, so let's see what little areas do I have this time. From -5 is right here. Okay, so that's going to go up to here. And I've got the cutoff here at -3, right? So that's a rectangular region, and it's above the axis. So I will have what the height here is 6, and the width is 2. So I have an area of +12, 6 times 2. Right? Also, I can split right here, and I'll have a triangle and a square. 3 times 3, I'll have a +9 area here, and then another 3 by 3 triangle, which will give me +9 halves. All right, so then for this antiderivative, for this integral, for this signed area, I've got a negative, and then I have 12 plus 9 plus 9 halves for a grand total of negative, let's see, that's 21 plus 4.5, so 25.5 negative, right? Okay. G prime of -2. Now wait, let's think for a second. What's G prime according to our fundamental theorem? The derivative of the thing that has x in the integral is just g of x. So what's g, little g, of -2 is what this is, right? What is that? Little g of -2 is up here. It's here at 5. Right? Let's think about that for a second. I'm gaining is what this is saying. My derivative is positive for capital G. That should make sense to you, because as I'm pulling this way, notice as I went into the negative regions, I was at a negative value for big G, right? But big G of 0 is not negative, it's 0. So as I go along this way, I should have an increasing capital G value. Well, that makes sense. Capital G's derivative is positive at that point, and along many of the points there. Next question. Where does the derivative G prime, capital G prime, equal 0? Well, that would be important because that would be the critical values of capital G prime. Or just capital G, So where, remember, G prime is just little g, right? So where does little g of x equal 0? Well, that would be right here and right here. X equals 3 and x equals 12 would be my answers here. Those are my critical values of capital G. Where is capital G a maximum? Well, remember from our first derivative zones, if we know that we have some critical values, right? Okay, I've got x equals 3 for this critical value and x equals 12 for this critical value, right? Okay. G prime is little g, yeah? So little g is my derivative. Okay, so over here, all I need to do is pick some value, like what's little g of 2? And I don't even care about the number, but we can figure that out, right? Little g of 2 right here. Looks like it's right at 1. equals 1, right? My derivative is little g. It's positive. That means that this is increasing on a whole interval. There's a whole interval of increase up to x equals 3. Next, between 3 and 12, pick any number you want, right? Any number you want. How about little g of 6? Little g of 6 is negative 3. The derivative is little g. It's negative. This is a decreasing region between here and here. Guess what? There is no past 12, right? The function stops at 12. But get this. Big G is increasing until it hits x equals 3. Then it's decreasing. Increasing, decreasing. X equals 3 is in the middle. Guess what? X equals 3 is my maximum. Big G of x equals a max when x equals 3. So that's the relationship there. You just have to remember that little g, the graph that we're looking at, is a graph of a derivative in this case. And the way that my function is defined, I can use areas to find big G function values. And little g is just the derivative values. Okay? I hope this has helped you understand the fundamental theorem of calculus and how we can now calculate all of the integrals. From here on out, what we'll be doing is applying a lot of our ideas of just using integrals to do areas or to sum up functions over intervals. And then eventually we'll just be talking about how to do integrals of all of the other functions.